In this segment, we're going to look at correlating electrical usage to PV requirements so we can go from energy load to photovoltaic supply. The goals of this lesson are to define the difference between calculating for annualized energy and the percentage-based energy planning using solar. Use a solar installation map to identify daily and annual average solar energy levels from a given location. Calculate the number of photovoltaic panels required to serve an annual energy demand using a simplified efficiency limitation of solar PV systems. And finally, perform a basic calculation defining the solar power requirements to serve an energy demand. Let's go to energy demand. In the previous video, we looked at several ways to determine energy demand of individual appliances. These included using a power meter, looking at product labels, and online resources like the Energy Star website to determine instantaneous power when in use. We then had to estimate the amount of time the appliance would be in use during the year to calculate the annual energy demand. A simpler way to determine energy demand when dealing with a grid-tied building is to use a utility bill. Remember that energy demand use is an annual event, but it does vary day to day and possibly month to month or seasonally. So while we could calculate daily energy use, we typically plan solar for annual demand. The only time daily variations in energy is critical is if you're working off-grid or need to make sure that a battery or a photovoltaic system can support the maximum daily energy demand. Let's consider this example of an annual usage of 12,000 kilowatt hours, an energy demand that's a little higher than the average United States customer. One way to look at energy demand and photovoltaic system design is to plan on replacing 100% of our energy from a traditional utility with solar. So if we use and pay for 12,000 kilowatt hours per year from our utility, then we would want to produce 12,000 kilowatt hours of electricity from the PV system during the year so we come out even. Now that's 100% of our annual demand. Because of net metering, it does not mean that we have to produce 100% of the demand each day, just annually. So we'll discuss net metering in a future lesson, but it's essentially a financial system that allows you to sell excess electricity to the utility when production exceeds need, but purchase that electricity when the PV system is not meeting the electrical load demand. In other cases, we might want to look at installing a system that's a fraction of the total electrical need. This is going to be dictated sometimes by cost limitations. Maybe we can't afford a system that's large enough to supplement 100% of our energy. Or space limitations. Maybe the rooftop or the ground area is too small to accommodate a system that large. There's also oftentimes both financial and electrical limitations for producing more than 100% of the electrical need. You can't produce more power than your electrical system can accept, and several states limit the payback on production to no more than maybe 100 or 110% of your annual electric load. Otherwise, you end up being what's called an independent power producer. So review your federal, state, and local rules to know your maximum allowable photovoltaic electricity production. Now that we know how to calculate annual energy demand, we're going to move forward and look at sizing the whole photovoltaic system. Solar energy insolation, or incident solar radiation, varies across the globe and varies due to differences in latitude as well as climate. Oftentimes these are connected though. Places that are hot and sunny tend to be in lower latitudes closer to the equator, and places that are cooler and less sunny tend to be further from the equator at higher latitudes. However, there can still be a lot of variation because of local geography. We're going to need some sort of mapping tool to help us understand that total insolation value. Several resources are available, but at this point, we're going to look at just one simple online map that I've downloaded from the United States National Renewable Energy Lab, or NREL. This map of the United States is color-coded to show what areas have high amounts of sunlight, which are red and orange, and low amounts, which are green and blue. We'll come back to this map in a few moments, but first, let's take a look at how to use the map of sunlight and begin to connect it to the photovoltaic module. So how do we size for photovoltaic power? Meaning, how many modules do we need to plan for? Well, photovoltaic power output depends on the sunlight level. That means that the more power that comes out of the panel will occur if it's sunny out, and less power comes out when it's cloudy or nighttime. Photovoltaic energy, which is a time of use measurement, combines the hours of sunlight and the intensity. So you could have a low intensity for a long amount of time, or have a high intensity for a short amount of time, or any variation on that. It's very much like the hairdryer and the light bulb analogy that we've previously discussed, and why we're again going to focus on energy. Photovoltaic modules are rated by power, and that value is the power output under standard test conditions. As we discussed previously, that corresponds to a sunlight intensity of 1,000 watts per square meter at 25 degrees Celsius. This means is that a PV module in a sunny place with lots of daylight hours produces more annual energy than the same panel in a less sunny location. So more sunlight power in multiplied by a specific amount of time means more solar energy and solar electricity. Things are not as simple as just looking at the energy of sunlight though, or the panel power, because we also need to think about efficiency of the system. Photovoltaics have an efficiency of about 10 to 20%, a concept and calculation that we reviewed in Module 1. That means that only 10 or 20% of the light that hits the panel is actually converted into usable electricity. Luckily, that's already factored into the power rating on the panel. Aside from that internal efficiency of the solar panel, there are losses from things such as wiring mismatches from junctions and differences in wire sizing, the inverter, which converts the direct current to alternating current, as well as simple things like dust that falls on the panel's surface, which lowers the amount of sunlight available to be converted. Another efficiency limitation is temperature mismatch. Panels are rated under test conditions, 25 degrees Celsius, about 77 degrees Fahrenheit. In reality, when it's sunny outside, the actual temperature is usually much higher. What's interesting about photovoltaic panels is that when the temperature goes up, the efficiency goes down. So overall, between the wiring mismatch, dust, temperature losses, a module loses about 10 to 20% from the nameplate or panel rating itself. So the true power that's delivered by a panel is only about 80 to 85% of what's listed. So we need to plan for that as we size our system. So let's look at an example where a photovoltaic system produces 10,000 watts of electrical power. Because of the external efficiency limitations, only 80% of that power can be collected, or 8,000 watts. So we always need to oversize a system to overcome that external efficiency limit. So if we truly wanted 10,000 watts to be delivered to our home or our building, we would divide by 80%, and we see we actually need a system that's rated at 12,500 watts, a little bit larger. So what's the next step? Well, we need to go from the electricity load, which is how much PV electricity we need to supply, to the sunlight energy that's available, and then calculate the size of the photovoltaic system. We're going to look at just the very basic approaches to this at this point and look much more in depth in subsequent courses. So let's jump back to that insolation map and look at the resource that's available to us. We're going to use an example where we have around 5.5 kilowatt hours per square meter of sunlight, which is also known as full sun hours. A full sun hour is defined as the solar insolation a particular location would receive if the sun were shining at its maximum value for a certain number of hours. That maximum value is defined by the standard test condition of 1,000 watts per square meter. So, according to the legend on the map, this value of 5.5 full sun hours shows up at about an orange color. That orange color corresponds to somewhere around the southern Midwest, Oklahoma, Texas, in the United States, as well as much of the west coast of California. Since we need annual sunlight energy, we're going to have to multiply that daily full sun hour level by 365 days to get the total annual energy or total annual full sun hours per year. So if we do that and multiply 5.5 by 365, we get 2008 full sun hours, the annual sunlight energy that's available. We then divide the 12,000 kilowatt hours of electricity demand of our energy by that full sunlight hours of 2008, and then divide again by the external efficiency loss of 80%, or that we get 80%. So we divide by 0.8. So that's the efficiency of the system after we take into account those losses we discussed previously. The calculation tells us our photovoltaic system size needs to be about 7.47 kilowatts to supply the annual 12,000 kilowatt hours load in a location that receives 5.5 full sun hours per day. So what does this mean? Well, if you look at the popular press or news clippings, it might say a 10 kilowatt system was installed or a 1 megawatt system was installed. These kinds of numbers are talking about the installed power of the system. But remember, that power doesn't actually tell us anything about the energy that's produced. If we take that same size system and put it in the Northeast United States, it will produce less energy because there's less sunlight. Sunny areas in the Southwest United States will produce more energy. So this power rating gives you an idea of how much energy is produced based on sunlight levels. Now that we know the total power, the next step is to take that power and determine how many photovoltaic modules are needed to equate to that power. To do this, we take the total system power and divide by the power rating of the photovoltaic module you might use. In this example, 200 watts is a common size panel. So if we take the 7.47 kilowatt system and first convert it from kilowatts to watts, we get 7,470 watts. We then divide the 7,470 watts by the 200 watts per panel, which is, again, that panel rating. We come out to a value of 37.4 panels. We can't have a fractional panel, so we could round up or down depending on the situation. If we round down to 37 panels, we would be very close to achieving our need of 12,000 kilowatt hours per year. So there's an alternative option if maybe we can't afford those 37 panels or can't replace 100% of the load, but maybe we can replace 60% of the load. In this case, 60% of 12,000 is 7,200 kilowatt hours per year. So if we take that value and divide it by the same 2,008 full sun hours per year and the 80% efficiency, we come out to fewer panels and less power, only 4,480 watts. And if we divide that 4,480 watts by the 200 watts per panel, well, then we get only 22.4 panels. So if we were to connect about 22 panels together, we would get about 60% of our annual electricity load covered by photovoltaics. So in review, we start by looking at the total electrical energy load. Then we look at the sunlight level for the location we're in. We then divide the total electrical load by the sunlight hours and the system efficiency. That will give the size of the photovoltaic system power. We then take the size of that photovoltaic system and divide by the power of the individual module, and that gives us the number of total modules required to support that original electrical load. So in summary, you should now be able to define the difference between meeting annual and percentage-based energy loads using solar energy. We should also be able to use a solar insolation map to define the daily and annual average sunlight levels for a location. You should understand some of the basic limitations to system efficiency and be able to incorporate those efficiency values to determine the system power. And finally, be able to determine the number of modules to serve a given electrical load in using a basic calculation.